we are going to be talking about momentum this week. It's our first unit. And there's a lot to momentum. So in your lesson, it's going to include something called force and impact, which is something that is it's hands in hand with momentum. But for today's lesson, for the whole group lesson, we're really just going to focus on momentum. We're going to focus on, I'm going to introduce the equation. So just so you know that when you're getting to the lessons for this week, you may come across force and impact and you may think to yourself, we didn't go over this in whole group, but rest assured, I have warned you that we are not going to go over that just because I wanted to focus on one idea first, and then you guys can tie in that in later. Make sense? Okay, so let's get into momentum. So we've got this whole idea. The first thing I want you guys to do, though, is tell me how you're feeling. How are you feeling today? Right? And then this should have an answer, right? So I'm going to show responses. So we've got some answers going. Good. Tell me how you're feeling. You're feeling good? Give me a little bit more description than that. Are you feeling great? Is there a reason why you feel good? Did you have a really good sleep? You feel rested, good-ish? Okay, fair enough, fair enough. Good. And these are anonymous, so I don't know who answered. Okay, so you're feeling good-ish. All right. Hey, TJ. If you please see that I am recording, so it's up to you whether or not you want to turn your camera on or off. And then also the link to our Pear Deck is in the chat. So if you just click on that link, it'll get you connected to us right away. And the first question of the slide is, how are you feeling? So I'm going to wait for you to join TJ, and then we're going to get started on the rest of our slides. We've got quite a bit to get through. And per usual, feel free to take notes. Feel free to listen. Like we said, this video is recording, so you can always come back to it if you ever miss anything. All right, TJ, let me know if you need help with that link. We're going to go ahead and move on. So we are feeling good and good-ish. That's fair enough for me. I'm right there with you, ladies and gentlemen. So let's go ahead and jump right in. Awesome. We do have 3 responses. Yay, we've got 3 people. Awesome. Okay, so today's agenda, I'm going to make some general announcements. I'm going to go over the quarter 4 schedule, except I'll have to do a quick switcheroo. And then we are going to start with our warm-up, and we're going to get right to that intro. So a little bit of backstory for us, but we'll get to it quite quickly. Okay, so where are you? I lost you. Okay, so a couple of announcements. Remember, when it comes to attendance, we have a whole group. I recommend coming to one whole group, at least one small group, and one help session if you need it. Remember that small groups are the same lessons. So that way, if you can't make it to one, you'll be able to make it to another. There is on the pacing guide about 1 to 2 lessons per day. So that's about 2 hours of physics work. And then remember that, come talk to me if the pacing is up too fast, too slow, whatever the case may be, just contact me. Let's communicate so we can figure out a plan together. And then important announcements in Fuel Ed. Remember to turn on your notifications so that way anytime I post something in the announcements page, you don't miss it and you get that information in a timely manner so you know what's going on in the class. So make sure that you've turned on those notifications. This is Miss Kirsch's schedule. So it's similar to mine. Let me just go ahead and tell you a little bit about my personal schedule. So we've got, oh my gosh, does she and I have the exact same schedule? We really do. So physics, remember that Monday help session is going to be it's going to be at 11 o'clock. We're going to be talking about the lesson for the week. We've got our whole group at 10. We've got our first small group on Wednesday at 11 o'clock. The only difference here is that I also offer a physics group at 9:30 on Thursdays. and again at 1 o'clock on Thursdays. And then I actually do not offer a physics help on Friday. So that's the one difference. She offers it on Friday. I do not. So, and all help sessions that are available to everyone. So that's the schedule. All right, so we've got our first pacing guide of the week. So this is what we have to look forward to. I remember that I said I was going to put the labs in the same day. So keep that in mind. That's a change from what I've already posted. So lesson 6, lesson, what is it? 1.6 and 1.7 are going to be moved. Oh, they already are on the same day. I think I was going to, what am I saying? It's already on the same day. I'm good then. Losing my mind already, you guys. First day. Okay, and then you can also see the due dates in Fuel Ed as well in the planning section. Awesome. Okay, let's do our warm-up. So here is a question for you guys. What do you know about momentum? When you think about the word momentum, what comes to mind? Maybe you've never heard of it before. Maybe you've used it out of not in a physics way. But go ahead and tell me a little bit about what you think of when you hear the word momentum. Good. My dog is yapping. She wants to be let in. All right, so I see that 2 out of 3 of you are responded. Remember that if you are here, we are all participating. Okay, you get speed from momentum. Good. Yes, there is speed involved. A ball rolling down a steep hill. Good. Yes. I know there are 3 of you here, so it's very easy for me to know if someone's not responding. So let's get a third response there. We'll wait a little bit. Why don't we get a third response? And I'm going to go let my dog in really quickly because she's has a really high pitch yap. And it's really bothering the neighbors. And yes, Madeline, you're right. I don't, but I can find out. But I will tell you I can. Okay. All right. So I guess we'll just have to move on then. So yes, these are great ideas. When we're thinking about momentum, we're thinking about movement. They were thinking about speed, right? We're thinking has anyone ever said you just got to get started and then you'll be on that momentum. You got to get momentum, right? Has anyone ever said that to you? So it is a conceptual idea. However, in physics, it is a very tangible, we can put a value to that momentum. So let's go ahead and move on to the next slide. And we can start to, we're going to go ahead and we're going to be watching a video. And we're going to watch this video and I want you to write down all the variables that you can measure. So think about what that means. What do we mean by variables? First of all, let's identify that term variables because it's been a little while since we've been in physics. So what do I mean by variables? And this time you can answer it in the chat because this isn't exactly a Pear Deck slide. Gravity, speed, momentum, good. Those are great examples. Yeah. So remember that variables are any sort of factors, right? They're what we can measure, what we can change, things that factors that are probably contributing to the situation, right? And then we're not trying to measure them, just what can be measured. So let's go in. So we're going to watch this video and you're going to write in the chat variables that we can measure. So this is the video. This is what I was telling you about. It's hilarious. I want to play this because the sound is really entertaining. I'm going to get an ad. So this one is okay. Tools, YouTube video. Here we are. So remember that we are trying to write down any variables that we can measure. All right, so we're gonna pause right there, all right? Go ahead and tell me in the chat, what are some things that we can measure? What are some things, variables of what's going on that we can get some sort of quantitative measurement? Okay, so what can we come up with? Friction, good, yes, awesome. Good, what else can we measure? What was he filling the soccer ball with? The weight, exactly. Abby, you're on the same page. Yes, the weight of the ball, right? So thinking about the mass, good. What else? What else can we measure? What do we think is going to happen? Let's take a look at that screenshot right there, right? We have an idea of what's going to happen. So what are we going to try to measure? The force, yup, good. What else? You guys kind of brought this idea up, this one variable up in the warm-up. Do you remember? When we talked about what are some variables, when I talked about variables, or when we talked about momentum, what else can we measure? Starts with an S. Speed and gravity. Exactly. Awesome. So yeah, so these are things that we can measure. So before we actually see what happens, let's take a look at some questions. Let's think this through. And go ahead and answer this in the chat. So let's think about the mass. Okay, so we're going to just focus on the mass right now. What do you think is going to happen if we increase the soccer ball's mass? So what happens if it's just air? What happens if it's filled with half of the water? And then what happens if it's filled with all of the water? What's going to happen to the ball's mass, right? So we're thinking specifically about mass right now. As the ball's mass increases, what do you think is going to happen? So in other words, if let's say if you're playing soccer and you've got a soccer ball filled up of just air, if you have a soccer ball that half water, all water, good. Yes, Madeline, the velocity is going to decrease, right? And why do you think that is? Right? So we're thinking velocity is going to decrease. If you're kicking a soccer ball and we're increasing the mass of that soccer ball, what do we think the result is going to be? Do we think it's going to be what are some of the effects from that? You think it's going to be, do you think it's going to be the same amount of force that you'll need to kick the soccer ball? Do you think you'll need to kick it harder? What's that going to do to your foot? Is it going to be really easy on your foot? Is it going to hurt your foot? Why would something that you are kicking actually hurt you back? You'll need more force. Good. Yeah, you might need more force in order to move something that has a bigger mass, right? Or if something that has a bigger mass hits you, it will generate more force, right? Good. And then what about velocity? What happens? What's going to happen if the ball's velocity increases? And remember, think about the video that we're about to watch, right? Think about this little thumbnail, this little shot right here. So what is going to happen, right? So what's going to happen if it's a slow throw, if it's a medium throw, if it's a fast throw? What do you think is going to happen? Think it's going to take less time, more time? Do you think it's going to be the same amount of time? And then thinking about momentum, right? Thinking about momentum, the faster the throw, the harder the ball hits. Good. And so if we're thinking about momentum, when we're talking about, oh my goodness, we've got momentum, we're on a roll, right? That's what many people use this term momentum for. And so we're going to learn we're going to figure all of that out. So these are just things to consider while we're watching this video. Okay. So we've got a couple of ideas about what's going to happen if the mass increases of the soccer ball. We're going to see what happens when velocity increases with the soccer ball. And so, what we realize, it's not just mass that's going to change it, and it's not just velocity that's going to change something. It's actually the two together. You guys mentioned this in the chat. You guys said that, if we increase the weight or the mass, it's going to decrease the speed, right? Velocity is going to be affected, but the same thing is going to be true if we were to, or the force was going to be harder, right? And the same is true. So we actually want to think of these things as together, right? We're hashtagging it. So we're doing a hashtag mass velocity. And these two things together is really what's going to affect what we're going to see. So now we're going to watch this video again. And while you're watching, I want you guys to be answering these two questions. Okay, each millisecond, the mass velocity of the ball decreases. What is happening with the mass velocity of the head, right? So remember, we're combining these two. So every single time the mass velocity of the ball decreases, okay, so meaning it's slowing down, what is happening to the mass velocity of the head? Okay. And the next question is, what is happening with the total mass velocity of the system? So these are two questions that we're going to be asking. I have them on the side. And, we're just going to watch the video without listening to the music. I think or the sound, I think it'll just be easier with the questions right next to the video. So that way you can see that. Okay. So we're going to watch this video. Or I guess it just takes us right to the thing. Why can't I? Why not? Right. I guess there's that. Let me go ahead and copy and paste. Can't. Can you guys hear it? You guys can't hear it?
No.
Okay. Okay. So this is where we left off. So remember, the two questions that we're asking is look at the mass velocity of the ball. And every single second that the ball decreases in speed, what's happening to the mass velocity of his head? Does that make sense? We can watch this a couple of times. Does that question make sense so far?
Wait, can you repeat that again?
Yeah. So every single time the soccer ball's mass velocity decreases, so the second is as it slows down, what happens to the mass velocity of this guy's head? Okay, that's what we're asking. Let me see 1 second. Okay, so then we're going to have a chance to answer it in a second. Okay, ready? You know what? I think it is more fun with sound. I changed my mind. I'm going to go ahead and put this in the video.
I just relax. Ready? I just relaxed.
Gets me every time. Okay, so remember the question is, right? Remember that the question that we're asking is, as the mass velocity of the soccer ball decreases, what happens to the mass velocity of this guy's head or face, if you will? So remember again, so when I'm talking about the ball slowing down, Okay, right? When we're talking about the mass velocity of the soccer ball, as it starts to hit his face, what happens to the mass velocity of his face? Okay. Okay. So Abby, you already started getting to it, which is awesome. So let's go back to our slides, right? So that first question, go ahead and respond. Each millisecond, right, the mass velocity of the ball decreases. What is happening to the mass velocity of his head? Right, so you were getting to that. So as the mass velocity of the ball is moving, and then as soon as it hits his head, then what happens, right? So go ahead and answer this question. Do you guys see the question on your screen when you are on it, or no? It does show up? No? Yes?
Yeah, I see it on
Okay.
the slide thing.
Yeah. Okay. So go ahead and write down what you're seeing is happening. So what happened as the soccer ball, the mass velocity, the mass in the soccer ball's velocity, as it was going towards this guy's head, right? What happened as the soccer ball reached his face? What happened to the face? And then what was happening to the soccer ball at the same time? Awesome. So the dude's head, the ball slows down. So then what happens to the guy's head? Yes, the ball slows down, but then what happens to the guy's head as the ball slows down? Yeah. Once the ball slows down, the ball slows down and force is applied. Good. Applied to what? Let's practice being a little bit more specific in our writing. So the force is applied to, and then what is going to his face? And then what happens to his face? Right? What's going on? Is it just like, oh, he just hits it and nothing else happened? That was it? Or was some things like, what was going on? Good. The force gets transferred to his head, smushing his face. Good. The ball slow downs and force is applied to the face, so his face moves to the side. Good. See, this is awesome. The more specific you can be with the more details, the better it's going to be awesome in your answers. Okay, so let's practice now. So when we get to the tests, we already know what that looks like. Awesome. So the ball slows down and the force is applied to his face. So his face moves to the side, or the force of the ball gets transferred to his head, smushing his face. I love it. Smushing is a very technical term, actually. But no, for real, that's great. Good. Okay, so we've got our first question, right? So now let's think about that second question. What is happening with the total mass velocity of the system? So we said in our first answer, right? In the first answer, we've acknowledged that the soccer ball is starting to slow down and that this force gets transferred to his head that makes his head and his face move. So then if we're talking about the entire system, so remember that the total system is both the soccer ball. So let's go ahead, let me get to write this picture. So the total system is his head and the soccer ball. So what's happening to the total mass velocity of this entire system? Okay, so what's happening? Is it changing? Is it increasing? Is it decreasing? Is it staying the same? Is it doubling? Is it tripling? What's going on with this thing, this mass and the velocity of the soccer ball? The total system being the soccer ball and his head, right? So is it increasing, decreasing? Is it not changing at all? Is it staying the same? Is it, okay, so the mass stays the same and velocity. Is it doubling? Is it quadrupling? What's going on? Okay, so the mass stays the same and the velocity increases. Good. And remember that there are no wrong answers here. We're really starting to just generate some observations and we're going to get to it. But really, it's important that you start to notice things on, you come up with some of the observations. Good. The mass stays the same as opposed to the velocity, which is increasing. Good. All right. Okay, so we're starting to see that there is a relationship, right? So we've got system 1, which is the ball in the head. Okay, so we've got system 1. System 2 is going to be the skull and the lips. So we're thinking about this as a unit, the lips, the skull, the nose. Where do you see things in motion stay in motion? Where do you see things at rest stay at rest? And I'm sorry, let me rephrase that. Where do you see things in motion stay in motion? Things are rest stay at rest unless acted upon by an outside force. So basically what we're asking is, where do you see Newton's first law? Is it the ball in the head? Is it the skull and the lips? Where do you see these actions happening? And you can answer this one in the chat. So where are we starting to see, Newton's first law? Maybe this picture will be a little bit more sense. The ball stays in motion until it hits his head. Awesome. Yes. And then what happens? So the ball is staying in motion until it hits head, right? So the ball is experiencing a force. And then what's going on with his face? What's going on with his skull versus his lips? Right? Yeah. So, right, if we watch that section of the video, okay, so pay attention to when things are moving. When is Newton's first law being applied, right? That's what we're really trying to figure out. What's staying at rest? Okay, the head moves due to the ball hitting the head. Yep, his skin and skeleton stays in motion. Good, exactly. So we saw that there was like a cascade of effects, right? We saw that as the ball hit his head and then the nose moved and then the lips didn't move until afterwards, right? So there is, because it was the force of, his face being moved, and then after his face being moved, then made his lips being moved. So we're seeing Newton's first law in action. All right, so let's look at the impact, right? So if we define the system as the ball and the head, where do you see things in motion stay in motion? Things are rest unless acted upon outside force, which you guys already identified. The ball slowed down and kind of came to almost a full stop, and then it got transferred over to his head. So we're going to move along. I also just noticed the time, and I've only got 20 minutes. So I want to make sure that we've got plenty of time to practice some of the math that goes with this. So as we are looking, go ahead. Oh, sorry. You know what? We only answered in the chat, so we're fine. Right? And then we answered this too in the chat, so we can move on. Okay, so it turns out we've been talking this thing about mass and velocity, but it turns out we've been talking about momentum the entire time. So we've got this word momentum, like you guys thought about it in the very beginning of the lesson. We started talking about this thing called mass velocity, and it actually turns out momentum is mass times velocity. So a couple of things. This is a really big equation that you're going to want to know. Really important is to know that P stands for momentum. Madeline, are you frozen, or are you just like really, okay, you're really just focused. Okay, good. Just want to make sure.
I'm here. Did I get frozen?
I know. I just want to make sure that we didn't lose you.
No, I'm still here.
Good. So we've got the lowercase letter P, and it is important to keep it lowercase because capital P means something else in physics. So lowercase p means momentum. That's what we're going to use, the variable we're going to use. And then we've got m, which is equal to mass, and v, which is equal to velocity. So the equation to momentum is mass times velocity, which is exactly what we started this whole unit with. But now we're just giving it the proper name. We recognize that as you increased the weight of the ball, or we increase the mass of the ball, it's going to have an effect. And if we increase the speed or the velocity of the soccer ball, it was also going to increase a force and an effect. So momentum is really just the mass of an object and how fast it's going. Okay, so now that we know this equation, and hopefully you guys have had a chance to write this down, we're also going to go ahead and take a look at this before and after. So where is the momentum before the collision? So this should be a multiple choice question. So thinking about this image, where is the momentum before? Okay, you've got 4 options. I don't remember exactly what they are. I made this yesterday. Oh, there we go. Momentum is in the ball. The momentum is in the head. Is the momentum in the head and the ball, or is there no momentum present? Right? So we've got 1 out of 3 people have chosen an answer. Again, where is the momentum before the collision? So this is like right before the ball hits the head. Where is all of the momentum located? Okay. Good. So we have the momentum is in the ball. Absolutely right. Before the ball hits the guy's head, it's all in the soccer ball, right? It's all in the football, technically. And there's nothing going on. He hasn't been hit yet, right? Good. Now, where is the momentum after the collision? So after the ball hits the head, right, they've made contact, where is all of the momentum now? Is it all in the soccer ball? Is it all in the head? Is it both the soccer ball and the head? Or is there no momentum at this point? Okay. So we've got 2 for the momentum is in the head. All right. So one thing that we need to consider, however, is the soccer ball, so they are in contact, correct? is the soccer ball still have mass, and does it still have velocity after the collision? Yeah. Now, does the face have mass, and now does he have velocity? Right? Does the face have velocity? It's moving. So then, yeah, it does. So when we're talking about where the momentum is after the collision, right at this moment, what can we actually say? It's not that it's all in the head. It is now the momentum is in the head and the ball. Exactly. Yeah. So we need to think about that. We need to consider the system, right? We talk about systems a lot in physics, and it really just means all of the components. So if we know, right, we've got momentum. Let me just see if the next, okay. If we have, right, so how can we convert these images that is representing momentum into an equation? We've got the before, we've got the after. We know that momentum can be broken down into, we know that momentum can be broken down as mass and velocity. How can we convert these images into an equation for before and after momentum? What do we think? What are some ways that we can change this image into an equation? And you can type this in the chat. So I don't think we gave it a slide. Okay, so Madeline, yes, so we've got P equals MV. Remember, we've got, so that's amazing. First of all, great, that is the equation. So then we've also got, right, we're talking about the before, and we're also having to take a look and think about the after, right? So we need to take into consideration these two objects and before they hit each other, and the two objects after they hit each other. So what is, so we know that P equals MV. Let's just focus on the before part. What could the equation be just for this part? We want to put them together. You've got P equals MV of what? What is the first thing that we're going to think of? The momentum of what? The ball. Good. Awesome. So we've got the momentum of the soccer ball. Then we've also got, we have to address the entire system. So you've got the momentum of the soccer ball. And then what are we going to do with this guy's face? Right? So we also have to consider P equals MV of his face, right? Now, we identified that the momentum is in the head and the ball in the after, right? So really what we're trying to say is the total amount of momentum here is going to be equal to the total momentum of his face over here. So I'm going to say the momentum of the soccer ball plus the momentum of his face equal to the momentum of the soccer ball and face. That makes sense? So really, it's really the conservation of momentum. It's the same idea as the conservation of energy, where what you start with is what you're also going to end with. The difference is just the transfer. So we've got this before. So the same amount of momentum. So remember, before, all of the momentum was in the soccer ball. All of it was in the soccer ball. None of it was in the face. However, they're both part of the system. And then over here, they're still part of the system, but now some of the momentum has transferred to his face and some of it still remains in the ball. So it's just the same amount of momentum. It's just transferring that momentum to one of the objects. Does that make sense? Yeah? Kind of, yeah. So remember, the soccer ball is moving a little bit still, but so is his face. So if we take a look at the video again, right at the impact of collision, what we start to notice is that his face is moving. So we know that this momentum from the soccer ball is transferring to his face. But the soccer ball is also moving. If you take a look right in this snapshot, it's bouncing off of his face. And now the water that was in the soccer ball is actually moving in the opposite direction. You can kind of start to see that right over here. So it's not like the soccer ball was moving, and then all of a sudden hit his face and just dropped to the floor, right? The soccer ball was moving a little bit too. And in fact, that was Newton's third law. For every action, there's an opposite and equal reaction. So as the soccer ball was hitting his face, transferring that momentum, that mass and velocity from his face, right, making his face now move, that was transferring some of that momentum to his face. However, some of the momentum also stayed with the soccer ball. So now we've got a total momentum here. Does that make sense a little bit? Madeline, do I got you?
So it's just like adding the two? Like,
yeah, so it's sharing it, right? So like think about when you're pushing a cart. Let's say you have a really big cart. If you're grocery shopping, you've got a lot of groceries and you hit another cart. You go and you ram into the other cart. Your cart is going to bounce back a little bit and it's going to cause the other cart to go flying. So what you're doing is you're transferring that momentum. You've got the mass and velocity of your shopping cart, and you're going to push some of that mass and momentum, or excuse me, that mass and velocity onto that second cart. It's the exact same thing. So you're transferring that momentum, but the momentum is going to be the same as it was in the beginning. It's just changing it to where the objects it's going to go to. Does that make sense?
so kind of like it's like the cart that's like pushing to someone else, it's like giving up some of the momentum to the other cart.
Mm-hmm.
Okay.
Yeah, exactly. But then if you add those two up, they're still going to be the same. So that's the biggest thing about this conservation of momentum. And then we're going to get into a couple of math problems in just a little bit. We've got 7 minutes left. So I'm at least going to get you started on a few. And then you can have access. I'll have access to the slideshow in a little bit. But the same amount of momentum in the beginning is going to be the same amount after. That's a really important key thing. Okay. So again, what we want to say is things to note. So if we look closely, we realize that the ball keeps moving after the collision, right? That's what I was just showing you. So we should consider it in after the momentum. It's still moving, so it still should be a part of that equation for after. And then the other thing we want to make note of is even if his head isn't moving much before the collision, we should still include it in our P before, our momentum before. Okay, so we're going to go into a couple of math problems that I think is going to help understand this a little bit more. And we're going to do it little by little. So let's first start with our equation. We're first going to start with the momentum equation. So P equals mv. So as we always do, we know our equation is going to be P equals mv, P being momentum and mass being, m being mass, v being velocity. We've got our equation. We've got our problem. A ball has a mass of 2 kilograms and travels at a velocity of 10 meters per second. What is the momentum of the ball? Did we not include a pear deck slide for this? Okay. So just go ahead and add it in the chat. If a ball has a mass of 2 kilograms and travels a velocity of 10 meters per second, what is the momentum? So we have to first list out our givens. So what does the equation give us?
The mass and the. Okay, what is velocity again?
Velocity is just speed with a direction. So we often use it interchangeably, but velocity just means you're going 25 miles west or 25 miles per hour to the right? So it's just a speed with a sense of direction with it. It's a good question, though.
Okay, because I forgot.
Oh my gosh, of course. It's our first day back. That's why we're doing a little bit of the warm start, right?
Mm-hmm.
So exactly. So we're given the mass and we're given the velocity. So then how are we going to solve for our momentum? What's the momentum going to be?
Do we multiply it?
We do. Yeah.
Okay, but for the velocity, 10 meter, is it meters per second?
Mm-hmm.
So you just do so would it be 20 meters per second, or would you have to convert some thing?
So great, good question. So the answer is 20, right? And so you're asking about the units. So whenever we're multiplying two numbers, we're also multiplying the units together. And in this case, there isn't a conversion. I know exactly where you're going with this. We're like, Newton is like the force per second or whatever it breaks it down to. This would honestly just be kilograms times meters per second would be the unit.
Okay, so then the momentum would be 20 meters per second, or would it just be 20?
20 kilograms times meters per second. You're just combining the units for this. Okay. Are you ready for the next one? Another more challenging one?
I'm ready.
Yeah, you are. Let's do it. Okay, so now we have a car with a mass of 1,500 kilograms that has the momentum of 50 kilograms times kilometers per second. What is the speed the car is traveling? So now we're going to do a little backwards work. We're going to do some rearranging of the equation, and this one does have a paradox. So you're going to put the answer in once you get it. So remember, we are solving for the speed, right? So how are we going to rearrange this equation, P equals mv, to give us the speed of the car? Yes, you are going to divide. Yep.
So it'd be 1,500 divided by 50?
Let's just double check. I'm not the best. Remember, I'm not great at doing it in my head. So if we know. Okay, so let's go ahead and fill in that equation. So you were really, really close. So if we've got P equals mv, we know that P, or momentum, is 50. We know that mass of the car is 1,500, and we are solving for V. So how are we going to get V by itself? How are we going to get V alone on that side of the equation?
So is it 1,500 divided by 50?
Other way around.
Oh, okay. So
Yeah.
that's 50 divided by 1,500. So
Yep.
it's 0.03.
Yep.
Okay.
Yeah.
Why is it going around though?
So if P equals mv, right? And then we've got, I'm going to be typing this as I talk. So P equals mv. We're going to go ahead, and we know we're solving for velocity. So we want to get velocity by itself. So how do we do that? We divide both sides by mass, right? Because mass is going to cancel each other out over on the right side of the equation where it's next to V. So then we're going to do P divided by M is MV divided by M, okay? Where M cancels out. So then you're left with P divided by M is equal to V. And then when we put in our information, our P is 50, our M is 1,500. So that's why we do 50 divided by 1,500 instead of the other way around.
Okay.
Yeah. Good. Great. Okay, are you ready for another one?
I have
Sure.
a question.
Yes.
So what if it was velocity times momentum? Would it still be like, what if it was velocity times momentum? Would it still be like P over the,
Well, I think I'm getting confused what you mean by velocity times momentum. I don't think in this situation, because I see the M, so do you mean mass? You're muted.
like, what if the equation was the other way around? Like, what if we had velocity and we also had momentum?
Oh, okay. If you had velocity and momentum, then you would do pretty much the same thing. It would be P divided by V is equal to M.
Yeah, okay. That was my question. Thank you.
Yeah. Okay. Yeah. Perfect. Great. Okay. Let's do one more and then we are going to be out of time. But the good news is we can continue this with small group. We can do some more math practice in small group. Okay. So now this is a very overwhelming slide. I know. So let's break this down really quickly. So we've got a large truck and a small car collide head on. Which vehicle will experience a larger change of momentum during the collision and why? So remember, we've got our before, we've got our after. So change in momentum is equal to the negative change in momentum of the car. Wait, I'm giving you the answers. Okay, what is it?
The change in momentum is equal to the change in the momentum of the car.
Yeah. That was not as exciting as I wanted it to be. I guess in Pear, this was supposed to be one of those, like it was blank, and then when I click, it was supposed to bring it in. I don't think Pear Deck lets you do that, I'm realizing. So yes, there is no change in momentum because remember that the momentum in the beginning of the collision is the same amount of momentum after the collision. It's just transferred. So it doesn't change. The momentum doesn't change. Maybe the mass and velocity would change, but the momentum itself would remain the same within the system. Kind of like the same exact thing that happened with the soccer ball in the head, right? All of the momentum was in the soccer ball in the beginning of the collision. And then after the collision, the soccer ball then transferred some of its momentum into the guy's head, but not all of it. It's the same thing here. It's the same amount of change in momentum. It's just going to be going in two different directions, which is why one would have a negative just to signify the change of direction than the other. Does that make sense?
Okay, what doesn't make sense is like all these triangles and letters.
So remember that the triangle represents change of. And then remember that the P represents momentum. So what this right here is breaking it down into specifics. So we've got the change of momentum in the truck is equal to the change of the momentum of the car, but the car is going in the opposite direction. Okay, so it's like it goes like this is what it's happening. Okay, so one is moving, and then when it changes, one gets moved into the opposite direction. That's what that negative is. Then it's what's happening in this second equation is it's breaking down that momentum. Remember our equation P equals mv. And so it's replacing the P with the actual equation. So now it's saying that the change of mass of the truck times the velocity of the truck is equal to the change of the mass of the car times the velocity of the car. So remember we were in the beginning of today's lesson, we were calling it mass times velocity, but actually that was actually momentum. So this is just breaking it down more and more for you. And then it just gives you that the mass of the truck times the change in velocity of the truck, because it's talking about the movement. The mass of the truck isn't changing, the velocity of it is equal to the mass of the car times the change of velocity of the car. Because again, the truck and the mass of the truck and the mass of the velocity isn't changing, the velocity is. And but that overall affects the momentum of both sides. And I see that, Abby. I do too, as a matter of fact. So with that, I think we're going to